It's a hopefully the work. Well, good morning, everyone. Today, our next session, and thank you very much for coming. Our presenter today is Changwoo. He's a final year PhD student. He is already funded, and he's graduating this May. He's joining Duke University as a postdoc this June. Changwoo is broadly interested in probabilistic machine learning models and algorithms on spatial and network data analysis. Especially probabilistic clustering is one of the recent research focus areas, the problem of discovering the latent structure of complex data sets with uncertainty quantification. Before coming to Texas A&M to get his PhD, he graduated from the Korea University in Seoul with a bachelor's degree in mathematics and economics. So let's welcome Changwoo.
All right, thanks for the introduction. Today I'm going to introduce the logistic data processes, which are useful for modeling dependent random probabilities with beta marginal distributions. So this is a joint work with Alessandro Zito, who is now postdoc at Harvard, and Professor Huyan Sang at Texas A&M, and Professor David Dunson at Duke. Okay, let's begin. So I assume everyone know beta distributions here, which is a continuous random variable supported on unit interval, which has a probability density function. It looks like this. So the beta distribution is really widely used for modeling random probabilities or ratio, thanks to their natural interpretations of parameters, and especially the conjugacy with popular binomial or negative binomial or geometric type of models. I'd like to emphasize the beta distribution's role in many Bayesian non-parametric models. For example, the beta distribution serves as a key component in the Dirichlet process mixture model, where DP mixture models tries to model the unknown probability distribution with infinite mixture of some specified kernel, for example, normal distribution with parameters mean and variance. And the mixture weights are defined as a stick breaking representation due to the Strauman's work. So each weights are defined as the product of beta distributions. So in this construction, the beta distribution serve a very important role in this DP mixture model framework. And let's more talk about the dependent Bayesian non-parametric model. So Bayesian non-parametric models provide a really flexible framework, and because not all data are IID, the dependent BMP models tries to model the probabilistic model in really flexible manner, but also allowing borrowing information from different sources. So this is often done by replacing independent components of BMP models with the stochastic processes that is indexed by some covariate X, which lies on this calligraphic X. So I'd like to introduce the dependent Dirichlet process model, where the dependent DP mixture model, the mixture weight, and also I'm only focusing on the covariate dependent weights here. So if we think about this DP mixture model with beta distributed stick breaking weights, the dependent Dirichlet process model can be constructed by defining the stick breaking ratio as a stochastic process that has beta marginal distribution. So this allows to model the conditional density estimation, where now the weight of the mixture model has covariate dependency, so that allowing borrowing of information across the covariates. So these type of stochastic process extensions of beta plays a very important role in many BMP models. For example, dependent polyad tree model, dependent Indian VPEP process model, and many others. So I'd like to focus on this dependent DP application example in terms of Bayesian density regression problem. So Bayesian density regression problem tries to probabilistically model the conditional density Fy given X with uncertainty quantification. So to motivate this Bayesian density regression problem, consider the following data set where X is the exposure, in toxicology data set, where this X DDE corresponds to the metabolite of the pesticides DDT, which are popularly used in pre-1970s, but banned because of its adverse effect on health. And here, the y-axis is the gestational age at delivery in weeks. So 40 weeks corresponds to the 10-week of pregnancy, 10 months of pregnancy. And one of the common interests in the environmental epidemiology and toxicology is to figure out the conditional probability of preterm births, where preterm births is defined as the gestational age of delivery is less than 37 weeks, given the DDE exposure level X. So we want to model this, we want to make an inference about this conditional probability, however, assuming minimally assuming the modeling framework in this data set. So think about just simply fitting the normal linear model. So in this case, normal linear model assumes the conditional density follows simply a normal distribution. And you can see in this QQ plot, these normal simple linear regression is too restrictive, and those assumptions do not meet in practice in real data scenarios. And Bayesian non-parametric models offer highly flexible specifications. So before going to the dependent DP, first think about just fitting a DP mixture model, modeling unconditional density for different subsets of data where, say, this orange data set corresponds to DDE exposure is less than 30, so that we estimate the density here. And similarly for the another subset of data and another subset of data. And we can see that the conditional density slightly changes, especially it's moving towards the left, which means there are increased increased probability of preterm births, which are defined as the area under this density estimate. And the dependent Dirichlet process model tries to model the conditional density. For example, given the DDE exposure level equal to this dashed line, which is defined as 0.2, 0.8, and it tries to borrow information smoothly across the different DDE exposure levels. So to get this conditional density estimate, we want to borrow information strongly from the data close to this DDE exposure level is in the specified level, and more weakly from the data that are far away. So I hope this gives a general idea on what the Bayesian density regression problems tries to answer. So one of the, as I briefly mentioned before, one of the main ingredient of this dependent DP mixture model is to come up with this VH term, which should follow a stochastic process with beta 1b marginals, which allows the covariate dependent weights, and that leads to the increased flexibility of the conditional density. And having this beta marginal distribution leads to the marginally DP at each X, which is a key for preserving the interpretability of the model and also preserving nice properties of DP mixture model. However, come up with this beta process is non-trivial. There are many different stochastic processes proposed. However, typically it leads to highly challenging posterior computation due to the complex specifications of this beta process. So today, I'm proposing the logistic beta process, which aims to satisfy these three desired properties. First, we want to build a stochastic process that can accommodate broad dependent structure on both discrete or continuous domain. So that discrete, for example, it can be a discrete time intervals, and continuous, it can be a spatial domain. And we want to consider a stochastic process that has a wide applicability. And also it should allow a wide range of strength of dependence from perfect correlation to the possibly negative correlation. And most importantly, it should facilitate the efficient posterior inference algorithm. And we propose logistic beta process whose logistic transformation leads to stochastic process with common beta marginals that satisfies these three desired properties. Okay, let's first start from the univariate logistic beta distribution, which is also called the type 4 generalized logistic or Fisher's G distribution up to the location scale reparameterization. We say the eta follows logistic beta with shape parameters A and B if its probability distribution is the probability density is defined as follows with support on the real line. And if the A and B are equal to 1, then it becomes a standard logistic distribution. And it is obvious from the form of the PDF that applying logistic transformation gives x to the a, 1 minus x to the b, and Jacobian term. So it gives a beta distribution after logistic transformation. In other words, if we have a beta distributed random variable pi, then if we apply the logit transformation, which is an inverse of logistic function, then we have a logistic beta random variable with parameter a and b. So the key component of the logistic beta distribution is relying on this normal variance mean mixture representation of logistic beta, which is due by Bandorf-Nielsen and others. That is, the logistic beta density can be represented as a hierarchical model where first we draw the mixing random variable lambda from Polya distribution, where Polya distribution is defined as, it is complicated. The Polya distribution is defined as an infinite convolution of independent exponential variable with different scale parameters. But just think about this type of, mixing variable. So this is the plot of the PDF of lambda. And given this mixing variable, if this lambda came in the variance term as well as the mean term, so that normal distribution have a mixture component enters in mean and variance, then the resulting distribution is the logistic beta distribution. And these are the corresponding logistic beta distribution where it can be skewed to the left or skewed to the right, and we can see the different shapes of the Polya distribution which serve as a mixing variable. We are building on this normal variance mean mixture representation to define a multivariate extension, which is actually not totally new, but also briefly mentioned in the original work of Bandorf and Nielsen and others. So consider the following multivariate extension. So we first draw lambda from same Polya distribution with shape parameters A and B. And we draw now the multivariate vector eta from the multivariate normal with the mean are just simply same as all dimension, but now the covariance is now lambda times the correlation matrix R. So because R has a unit diagonal, we can see that each component of the eta follows marginally logistic beta A and B. And we can see that logistic transformation applying to each coordinate gives multivariate beta distribution with beta AB marginals. And here the correlation matrix R controls the dependence. And this is the example plots of the bivariate logistic beta distribution with different correlation parameters. So here in the middle is the case when A and B are equal to 2 and 4 with correlation parameter equal to 0 in the middle. So in the top, it is a bivariate logistic beta, and in the bottom, it is the logistic transformed random variable. So the upper plot is supported on the plane, and bottom plot is supported on the unit square, 0, 1 times 0, 1. So you can see that as the correlation parameter changes, the logistic beta has different shapes, and the corresponding logistic transform random variable also have a different shape. And the most importantly, it has a beta marginal distribution at each dimension, beta 24, beta 24, beta 24, beta 24, but with varying level of dependency. So these are some, elementary results based on the normal variance mean mixture. So we can deduce the, okay. I think there's some. Okay, so this covariance can be calculated using normal variance mean mixture, where the psi and psi prime are digamma and trigamma functions. And one of the caveat is the being zero in the correlation parameter does not imply the independence, because we have a shared Polya mixing parameter. And if A and B are same, then we have a full range of correlation. So correlation of logistic beta can be reached from -1 to 1. But if it is asymmetric, the range are somehow limited in terms of its lower bound. So it has a non-trivial lower bound, which are actually different from the minimum possible correlation achievable from the Freccia lower bound copula construction. So I'm maybe come back in this detail later, but I'll save for the time. So building on this multivariate logistic beta, we can now define the logistic beta process with correlation kernel defined as the function with input x and x to the range -1 to 1. So we say eta follows the logistic beta process if its finite collection of realization follows logistic beta with shape parameter A and B and correlation matrix that has an element defined as the correlation kernel's function value. So same logistic transformation has beta 1 AB marginals, and it can be defined on discrete domain, for example, considering this AR1 type correlation kernel. Or we can also consider spatial domain, where this plot shows an example with Mach-Turn correlation kernel with range and smoothness parameter defined as 0.3 and smoothness 1.5. So this is a plot after the logistic transformation with shape parameters 2 and 4. So this also have a marginal distribution beta 2, 4. So it should have a mean 1/3, and it reflects the properties of logistic beta. And I'd like to also introduce the correlation kernel, special type of correlation kernel that are based on the normalized feature map. So if we think about the feature map, which is a mapping from the domain to the Q-dimensional space, where it is normalized in the sense that it has a unit Euclidean length. So it lies on some hypersphere in this Q-dimensional output space. And under this constraint, if we define the logistic beta correlation kernel as the inner product between two feature map vector, then it satisfies the requirement to be a correlation kernel where the x and x prime are same, then it has a unit Euclidean length. So the correlation kernel requirements are satisfied. So these are the example of the normalized spline based on the normalized spline basis functions. So consider the following domain X, which is defined as a DDE level, as I shown in the previous example. So our domain X is interval between 0 and say 150. And we can consider the spline basis functions with 6 degrees of freedom. So the output has 6 different splines. However, we want to normalize them such that it has a unit Euclidean length at each x. So the dashed ones are unnormalized spline basis function on this domain, and we can normalize those feature maps can be casted on the logistic beta process, which requires the kernel to be a correlation kernel. Under this special correlation kernel defined with normalized feature map, there are some interesting representations. First is a hierarchical representation. So with the normalized feature map kernel, we can express its n-dimensional realization as a mixture similar to the mixture representation, where we draw lambda from Polya distribution, and we draw the random variable gamma from the standard normal distribution, the Q-dimensional standard normal, and then the logistic beta realization is simply as follows. And we can see if we condition on the Polya random variable, now the logistic beta is parameterized by the Q-dimensional normal coefficients, so it clearly shows a dimension reduction from N to Q based on the Q-dimensional feature map. And another representation is linear predictor representation. So if we consider marginalizing out the lambda in the previous representation, then we end up with this formulation where we have if A and B are all fixed, then these are all fixed intercept with varying. So this is a fixed varying intercept term, and we can view this basis matrix phi as a design matrix, and this beta corresponds to the coefficient on the design matrix, which assumed to follow the logistic beta with identity correlation matrix. And this corresponds to the linear predictor representation, because if you think about the Bernoulli response model, so that the logit transformed probabilities are success probability of Bernoulli, then we can see the eta is a linear predictor with LB coefficients with fixed varying intercept. So this resembles the basis function representation of the Gaussian processes, also popularly known as the weight space view of GP. Okay, so these are all the specification and examples of logistic beta processes, and let's dive into the actual statistical model. So perhaps the simplest possible example is just a binary data. So we assume we have a binary data Z indexed by X. So GXI are binary random variable that are assumed to be independent realization from Bernoulli distribution, where the success probability is sigma eta xi. So here, if we introduce the logistic beta process prior to the logit transform probability, so sigma is a logistic transform. So after logit transformation, this eta is a logit transformed probabilities. Then it leads to the marginally beta AB prior on success probabilities, which are defined as probability of Gx is equal to 1 at any x. And the main goal is to make an inference on the eta of x star at arbitrary x star, including xi and new xi value, but with efficient posterior computation. So for example, this is the previous plot on the logistic beta process realization after logistic transformation. And assume we have those binary data on the domain 0 to 3. So we have a binary data densely here, zeros in here, but sparsely in the middle, and densely in here, and densely in here. Then we want to make a posterior inference so that this black line corresponds to posterior mean, and shaded region corresponds to 95% credible interval. And if we can see it well estimates the true underlying success probability function, which are here, the dashed line. So to see how the logistic beta process can achieve efficient posterior computation, the aim of the quantity of our aim is to draw samples from this posterior, which is prior times likelihood, which is expressed as follows. And if you look closely in the likelihood term, there exists a popular data augmentation scheme using Polya gamma augmentation, which converts this likelihood term into the conditionally normal likelihood. So by introducing this augmented likelihood function, where conditionally on eta, the omega follows Polya gamma, and conditionally on the augmented auxiliary variable, we have eta follows conditionally normal distribution. And because LBP eta is defined as a normal variance mean mixture representation, we have a conditionally normal prior condition on the mixing variable lambda. So eta LB prior is actually also the conditionally normal. So we can exploit the normal conjugacy for the full conditional distribution P eta given omega and lambda, which are also multivariate normal distribution. So this is the one cycle of Gibbs sampler under the simplest Bernoulli latent LBP model. So we update the poly gamma auxiliary variable, and we update poly mixing variable, and we update latent LBP parameters from its full conditional distribution, where now we can see the eta is sampled from the multivariate normal. And the poly mixing parameter is a little bit, tricky. And can we do better instead of drawing sample from this full conditional lambda? We can actually perform better by considering the following collapsed conditional distribution, so that it actually jointly updates the lambda and eta. So this results in the blocked Gibbs sampler, where blocking is possible due to normal conjugacy, because LBP is normal mixture and likelihood is conditionally normal, so we can collapse the middle term. So we end up with this blocked Gibbs sampler. And still sampling lambda from this lambda from the distribution that are proportional to the product of polya and normal might be somewhat tricky. And we are using the Metropolis Hastings sampler to sample lambda, which is just a univariate quantity. However, we want to leverage the following identity between the polya distributions because the polya distribution density is quite complicated and can cause the numerical issues. So for example, if we go to the polya density, which is actually expressed as a alternating series form, and this alternating series form of density can cause numerical instability, especially evaluating near the origin. So we can leverage the following polya density identity so that we can define the proposal distribution as this polya A prime B prime, where we select this A prime B prime parameter as adaptively based on the running averages of lambda. So there are many different possibilities, but one of the possible way is choose the new A prime B prime value to be to match with the running averages, so moment matching criteria sort of thing. So this, most importantly, this avoids polya density evaluation because there are the ratio between polya, the proposal and polya prior is now can be represented as a closed form. So this is some computational trick involved in the updating the mixing variable. And also, if we deal with the large data set, like n is like 1,000, then we may have some problem with the scalability in terms of evaluating this multivariate normal and drawing random samples from this multivariate normal. However, because polya, the LBP is defined as a mixture of GP, so existing GP computation strategies can be easily applied to those computation strategies for LBP. So for example, if you think about low rank structures of the correlation kernel, which is normalized feature map, then the step 3, which is sampling from n-dimensional normal, becomes just sampling from q-dimensional equivalent parameterization. And if we can also think about the modified predictive process type model, which is basically assuming the correlation is low rank plus diagonal. And we cannot leverage all the Woodbury metrics formula to quickly evaluate the inverse of this low rank plus diagonal term. And let's compare with the other approaches that induces beta distribution. So this is another possible way to achieve the dependent probability modeling with beta marginal by considering copula. So Gaussian copula, assuming this latent zeta random variable is drawn from multivariate normal with unit variance, and the corresponding quantity is the success probability of Bernoulli by considering copula formulation. However, under this copula formulation, although we have a still marginal AB prior, beta AB prior, but the corresponding posterior is very scary, and even in this simple Bernoulli model, and hardly generalizable to the more complex models. Okay, so far we describe how LBP can achieve efficient posterior computation with Gibbs sampler, and let's go with more complex models where now we are trying to build this beta process, and we can replace this with the model by modeling logit transformed V with logistic beta processes. So because logistic beta process can be defined on any discrete or continuous, it has a rich dependent structure, and it also comes with efficient posterior computation for this logistic beta dependent DP. So I'll skip this for the time being. So to see how LBDDP still maintains the tractable posterior computation, and we can see that the infinite mixture of normal, it is not to be necessarily normal, but infinite mixture normal, its mixture weights are now the sample specific assignment probabilities, and the main trick is using this continuation ratio scheme. So based on this stick breaking representation, we can convert or interpret these stick breaking weights by the conditional probabilities. So first stick breaking ratio is the probability that assigning to the first mixture component, and V2 can be interpreted as conditional probability of assigning to the second component, given that the first component assignment has been already made. So and so on and so on. So based on this continuation ratio scheme, this is equivalent to the sequence of latent LBP models. So the assignment, whether being first component or not, can be treated as a Bernoulli likelihood, and second component can be treated as a Bernoulli likelihood conditioned on the data that our component assignment is greater than 2. So there are lots of specific insight, but the main idea is the corresponding Gibbs sampler has independent the latent LBP binomial data in its inside. So if we think about the block Gibbs sampler, then the step 2 is actually the same as the previous block Gibbs sampler that I introduced before, but now with H-1 different latent LBP models. So for step 1, updating is just simply updating the indicator with the truncation level H. And step 3 can be done with conjugate priors for G naught. And these all procedures are similar to the recently proposed Polya gamma data augmentation for logistic process by Ligon and Durante, but with only the step 2.2 are added by updating the Polya mixing parameter. So to illustrate the computational benefits and flexibility of the latent the logistic beta process, we can consider the following simulation by considering the spatial domain. We draw the binary random realizations from 400 data and keep the 100 test data, and we generate the data from Maton correlation with fixed smoothness parameter. And we compare the data that are generated from latent LBP model and Gaussian copula model with different range parameters. So first aim is to assess the benefits of the posterior inference strategies. And the second aim is to compare the predictive performance of this logistic beta process-based model. And this is the simulation study result in terms of mixing behavior of the lambda. So by assessing the benefits of the posterior inference strategies involved in LDP. So you can see that ESS, effective sample size, higher the better. Effective sample size per second, of course, higher the better, and acceptance rate, higher the better, because we are using the independent metropolis Hastings sampler, not random walk. So we can see the blocking strategies and the adaptive Polya scheme both improves the mixing behavior of the algorithm in all different data generation scenarios. And second aim is to compare the predictive performance and computational advantages. And we consider data generated from the Gaussian Coppola model. So we fit the latent LBP model, but we generate the data from Gaussian Coppola and fit the Gaussian Coppola model as well. And we compare the result in terms of RMSE and mean continuous rank probability score. And you can see that training test RMSE are really similar. So the parenthesis is Monte Carlo standard error. And Gaussian Coppola works better because the true data are generated from Gaussian Coppola, but we can see the training and test errors are really negligible. However, one of the main benefits come from this sampling efficiency defined as multivariate effective sample size per second. So higher the better. And we fit the Gaussian Coppola model with STAN, the highly efficient Hamiltonian Monte Carlo algorithm. And our latent LBP model is coded with plain R. And we can see in terms of multivariate effective sample size per second, we achieve much better sampling efficiency compared to Gaussian Coppola model that are coded with Hamiltonian Monte Carlo. Finally, we revisit the real data that I introduced in the beginning. Because there are no publicly available software for dependent distributed process with covariate dependent weights, the continuous covariate dependent weights, we compare with another dependent stick breaking model called logistic stick breaking processes, which are really similar to the logistic beta DP, but it is not dependent DP in the sense that it does not maintain marginal DP. So we try to analyze the preterm burst probability based on two subgroups of data, based on smoking status, yes or no. And we run MCMC with 350,000 iterations, which ran in less than 10 minutes in my personal laptop. Here the sample size is around 1,000. Here are some specific on the setup. So we consider the normalized lateral spline basis with 6 degrees of freedom. So we effectively decrease the dimension of the LBP to 6. And these are the hyperparameter settings, which leads to very similar co-clustering, prior co-clustering probabilities. So these are some details of the real data. And this is the result that are compared with the logistic breaking processes. So above is the proposed LBDDP mixture model, and below is the logistic breaking process model. Here, the x-axis is the exposure, DDP exposure level, and the y-axis is the probability of preterm burst defined as the y is less than 37. So as x increases, as the exposure level increases, we can see the increase of the preterm burst probability in all hyperparameter settings and all different models. However, there are some subtle differences, especially across the different hyperparameter settings. So the first column, second column, third column corresponds to different hyperparameter settings, but they are tuned so that the first column share the similar prior co-clustering probability, and second, this two corresponds to similar prior properties and so on. And you can see that although the LBDDP results are not that much different across the hyperparameter settings, we can see that LSVP, logistic breaking process, which is not dependent DP mixture model, has quite a lot difference in terms of the estimated probability preterm burst in terms of the uncertainty quantification. So we can see that the credible interval at the high exposure level is really smaller compared to the other settings, and it becomes more wiggly and becomes more smoother. So LSVP are really sensitive to the hyperparameter choice, and they're typically hard to pick in advance. So these are similar plots based on the non-smoking data. So compared to the smoking data, we can see the preterm burst probability is slightly decreased. And the main observation is, although the proposed LBDDP model does not have a sensitivity across hyperparameter settings, we can see the very different uncertainty-led quantification results with the logistic breaking process model. So to conclude, we proposed the logistic beta process for modeling dependent beta random probabilities, which can address three different properties. First, accommodating broad dependence for both discrete and continuous domain. Second, allowing a wide range of dependence strength from perfect correlation to possibly negative. And finally, it facilitates efficient posterior inference algorithm by leveraging the normal conjugacy. We apply LP to DDP mixture model where dependent beta plays a crucial role, and it has a full flexibility, clear interpretation, robustness to the hyperparameter settings, and computational tractability, which is a rare feature with covariant dependent weights. And we can also consider applications to covariant dependent clustering and other dependent BMP models, for example, like dependent Indian whipping process, and beyond using the proposed logistic beta process. So this is the end of my talk, and I appreciate any questions you might have. Thank you.
Question? So you model dependent probabilities, right? So an ideal way to do that would be probably do some transformation on all the probabilities and make the probabilities lie in the whole of the real line and use some sort of Gaussian process or some elliptical process, right? So could you give some more insight into how we are getting a richer class of dependence being richer class of dependence that could be modeled by this?
Yeah, so the real line is just a simple example that I showed in this real data analysis example where we have a covariance space is the continuous real line, but because Gaussian process can be also defined on discrete domain, continuous domain, or just group-wise domain, which is simply just hierarchical group data. So in my understanding, you're asking how it can be applied in more general.
So you have so the process that you define is this more how is this able to incorporate a larger class of correlation and dependence structure compared to say simple like do a transformation and use the Gaussian?
Yeah, so that is related to the slide that I skipped previously. So because of the time being, I skipped one of the slide in maybe in here. So this is not the only way to, of course, model dependent random probabilities with beta marginal. And so formally, the logistic beta DDP is defined as a collection of dependent random probability measures. And we compare the range of the richness in terms of range of the correlation between random probability, the Borel sets evaluated on the Borel sets. So maybe the most simplest but harder to treat is the copula-based model that I just described before. So if we consider copula-based dependent Dirichlet process model, and so this left-hand side plot is the infimum, so lower bound of the correlation between two correlated beta random variable. And this is the corresponding correlation between the set evaluated domain. So we can see that in this plot, so the B is the second parameter of the beta, so L1 B here. So if B is equal to 1, so we have a symmetric A and B, then the logistic beta can achieve the full correlation range. However, as B is different from 1, for example, like 8, then actually the blue dashed solid line is the widest possible richness that can be attained by the copula-based construction, where this corresponds to the highly maybe next slide. Yeah, so exactly this plot shows how the different correlated beta has different realization. So this Breccia lower bound is the minimum possible correlation achievable. But however, the logis beta is this is the minimum possible correlation achievable by logis beta. So it has a limitation, of course. So but however, compared to like independent beta or correlated beta, it can of course offer the negative correlation, which are rare finding in the beta multivariate beta literature.
Thank you.
All right, thank you very much again, Ricardo.
Thank you for attending.